We'll start the next session, and we're very lucky that Michael Yampolsky is here as the next speaker, who's at the University of Toronto, and he's an expert in dynamical systems and also computability theory and complexity theory, and then will tell us today about work in that area. Thank you.
Okay. Working? Can everyone hear me? Okay, well, thanks very much. Obviously, I'm absolutely delighted to be participating in this and given this talk, and I'll talk about computability questions and dynamical systems, and subject that we worked on with Mark way back when, and I might actually mention a little bit of our old results, but my aim today is to talk about something else and talk about the subject of computability broadly and computational complexity and dynamics and so on. And I have a complaint because when I came up with the title of my talk, the talk in the morning was supposed to be computing with dynamical systems, and then very cleverly I made my, a play on that, and then the computing with dynamical systems got moved to tomorrow morning. So now it's a play on my title. So anyway, never mind. Look, this is obviously the this is a weather forecast, weekly weather forecast for Toronto. This is a very serious weather forecast that comes from the Canadian government. This is the Environment Canada, right? So we have to take this seriously, and now you can see the weather is not so bad. I mean, it's certainly not compared to February. I have a question to the audience. Right, so we'll look at this. This is pretty easy to interpret, right? So 23 degrees Celsius, for those who are unfamiliar with Celsius, you could still use your phone to convert to Fahrenheit. And, the clouds, the sun, all of this is good. 40% chance of showers, what does that mean? Yeah? Well, like what is it? What does 40%? Like, is it likely that it will rain today? What do you think? Toronto, it's here. Yeah. Yeah, it's not raining now. I can see that. And in fact, okay, so look, it's not really a trick question. Like, what's 40%? What is supposed to signify? What's 100%? Like, if it's 100%, is it gonna rain? And 0%, no rain, right? So we interpret this as a probability, right? So this is really probability 0.4, right? So it's, it might not. Okay, a serious question, a more serious question. Why is the answer given in such uncertain terms? I mean, this is, these people probably have a relatively infinite budget to run their models, right? I took this off their site just now, right? So can't they just give a yes or no answer? Why is it not deterministic? I mean, it's a deterministic question, right? Is it going to rain today, tomorrow? Why is the answer not yes or no? Well, I mean, people, they will always complain that they need more money, more budget, bigger computers. Why is the answer not deterministic? What's the difficulty? What's that? Sorry, I can't quite. Look, the answer that I'm looking for from you is that it's hard to predict the weather, right? We intuitively know that it's hard to predict the weather. In fact, the mere fact that it's hard to predict the weather was one of the main discoveries of dynamical systems in the 1950s. So this is the literally, I mean, the story of this discovery. What is this thing telling me? Okay, I don't want this. Okay, here is the actual discovery. So this was done by a meteorologist from MIT by don't remember the first name, last name was Lawrence, who studied a really simplistic forecasting model. This is actually a model of atmospheric convection. I mean, if you care, it's three differential equations. We don't really care about any of this, except I would like to point out that it is very, very mildly nonlinear. It is, if you look at it, almost linear. It has a nonlinear term x times z, and with a minus sign in the second line, and has x, y in the third line. ABC are parameters. I mean, this is really almost nothing, but cannot be solved explicitly. It's nonlinear. So he modeled it on a computer. The computers of the era were, not that great. So the following day, he wanted to repeat or actually extend the computation a little bit in the future, but instead of using the initial values, he took some intermediate values for the computation and discovered that surprisingly nothing worked. So what he obtained seemed to have nothing to do with the previous results. And here is an illustration. Okay, this is a three-dimensional system. I'm going to give you a two-dimensional plot on a two-dimensional screen of the trajectories of this system, right? So we're going to pick an initial value x, y, z, except it's going to be in the xy plane. And we're going to run this thing, and we're going to project. So you'll see trajectories self-intersect, which they're not supposed to do, and they don't in 3D, but this is a two-dimensional projection, right? So without further ado, I click here, and it runs, and this is a two-dimensional projection. So let me now clear this and do 2 clicks nearby. So I clicked almost in the same place, and of course you could see 2 trajectories starting close to each other, but then almost immediately divergent. You can see they are slightly different colors. So, but maybe you could see that, maybe you can't. But you should be able to see that the 2 curves are actually doing something quite different now, right? So they're indifferent. So this is, of course, colloquially known as chaos. This is extreme sensitivity to initial conditions. And this turns out to be in some sense typical in dynamics. And it's certainly something to expect when your dynamical system has a lot of parameters, such as a weather model. And so what this means in practice is that any initial error of measurement or any error of computation, of course, everything is done with finite precision. You could do it with a large precision, but still finite, will get amplified exponentially with time, which means that even short-term weather predictions, predicting weather a few days out or even a whole day out, 24 hours, becomes a futile exercise. It's you could probably do things with a good degree of certainty for the next hour if things are reasonably stable right now. But that's okay. So it's an objective problem. You can't. I mean, it's well known. It's it has been well known for a long time. It's in popular culture. There was what, a cow-tician in the first Jurassic Park movie, which is so okay. But I deliberately let that thing run as I was talking, and you could see that even though the 2 trajectories are being drawn sort of independently from each other, and they're tracing out the same shape. And indeed, there's the same 3-dimensional shape that these 2 things trace. This is known as a Lorentz attractor. Sometimes it's known as Lorentz butterfly attractor. partly because it resembles a butterfly, and partly because of his famous quote that butterfly claps its wings over Texas and there's a tornado in Brazil or something like this, and which illustrates the phenomenon. Right, so let's file that fact away for further discussion. So even though the way this limit in shape is being traced out is drastically different, the overall shape seems to be the same. Okay. Right. So that's why you cannot answer this with a certainty. Okay. So that's why these computations try to answer this somewhat tentatively. Okay, what is this 40% off? Like how? Like, look, it's an actual computation, right? I mean, it might be a rather sophisticated model and a big supercomputer, but what is this at 40% off? How do you get this thing to say 40%? Like, what does it literally mean? Yes, excellent. That's perfect. You know exactly the answer. This is known as a Monte Carlo simulation in general, right? This was pioneered by Stanislav Ulam when he was working on the Manhattan Project, and was first implemented numerically by John von Neumann. And in fact, if you go to the Wikipedia page of Ulam, then you'll see a picture of Ulam holding an analog Monte Carlo simulator for neutron diffusion, which was built by Enrico Fermi, so it's known as the Fermi. Okay, so I think I will So this is the extent of me using the computer today. I'm terrible with slides, so I'm going to write the rest on the board. Okay, so I'm going to stop sharing, close this. I don't need the screen anymore. So let's formalize a little bit of what the Monte Carlo method is. Okay. So first of all, even when we are modeling a system of differential equations, this is really a discrete time calculation, right? Any numerical scheme to do this will be discrete time. So let me just skip to discrete time iteration, okay? Instead of looking at continuous time models. So you have some ambient space, Rn, which n is probably large. You have some domain omega. This is your acceptable parameter values. You have some iteration scheme, capital F, from omega to omega, and you iterate, right? So you look at the orbits, F, A of X, and you want to say something about the statistical distribution of these orbits, right? So the Monte Carlo method numerically looks like this. You look at the full-on sums. So sum over, let's say, what am I using here? K, J. So K would go from 0 to n minus 1, and J would go from 0 to m minus 1. And in here, you are summing delta f a of x j, where x, j are randomly selected points in omega, right? Usually uniformly at random. And of course, the sums grow large, so you normalize. And now you expect that this will converge to a limit and statistical distribution, right? So this is the expectation of the method, that this converges to a limiting statistical distribution. And that's what you're sampling, right? The part of that distribution corresponds to rain and the part doesn't, and that's what you're sampling. You could just do exactly this to get your 40%. You know, you take a lot of points, you do a lot of tries, and you see in what percentage of the tries of the, a lot of iterates, and you see in what percentage of the runs of this you are going to get rain. Or you could do something more sophisticated. You build a large discrete Markov scheme, and then you have other ways. I mean, since it's a finite precision computation, in the end, it is a large discrete Markov scheme, and then there are other ways to get at this probability, right? So that's what you do. Okay, now there are questions both from the dynamic side and from the computability side. From the dynamic side, the question is obvious, like, can we typically expect something like this to be true and meaningful in some way, right? So if you just take a random dynamical system and some reasonably good class of dynamical systems, is something like this going to actually work? And from the computation point of view, the question is also obvious: can this be computed? Okay, so let's deal with the dynamical system side first. So there is a belief that something like this should generally make sense, which is not a general belief. And in fact, I don't think that we're going to be this lucky, but I will formulate this. So this is known as Pallas program. Named after Jacob Pallas, who formulated sort of explicitly, I think, in his talk at the ICM in I think late 1990s. And the Pallas program is as follows. So let me first make a definition. Let me say that mu is a physical measure for f if there exists a positive Lebesgue measure set of initial conditions A, well, maybe, I don't know, A sub mu. There exists A in omega such that the Lebesgue measure of A is positive, and for almost every x in A, the averages will converge to mu. Okay, so you take 1 over n sum delta, f k of x here. So x is an A, k again is from 0 to n minus 1, and this converges to mu. Okay? In the usual weak sense, that is, the integrals converge. Usually, you want to look at sort of indecomposable physical measures. So you ask that this would be ergodic. And the meaning is quite clear. I mean, it's clear why we call it a physical measure. This is something that you have a chance of observing in reality, right? If you roll the dice randomly and pick a point, then there is a positive probability that the point will be in the set A, and it will actually give you this answer, this distribution. A maximal such set A, I'll call it A sub mu, is sometimes called the basin of this physical measure. Basin of U. And Palace program is that typically there is a finite collection of physical measures UK such that the union of their basins is almost everything. Well, I didn't say that omega is 1, so this is almost everything. If this is true, then we expect something like a Monte Carlo simulation or a Markov map scheme or whatever, give us a weighted average of these measures, right? So the weighted just by the relative size of their basins. Okay, as I said, this is not necessarily true, but there is one set of results. I mean, one set of examples for which it's known that this is true, right? And this is perhaps the most famous set of examples in dynamics, which is also sort of the simplest set of examples in nonlinear dynamics you can imagine. These are quadratic maps of the interval. Okay. Oh, let me, by the way, comment that going back to the Lorentz attractor example is that in that case, it's known that there's only one physical measure. Okay, basin is everything. Everything is actually true. So for that particular system, and there is in fact a geometric rate for the convergence of this. So that all of this follows from a theorem of Warwick-Tucker. So in that case, you can actually sample using Monte Carlo and get pretty good predictions. Okay. And also, if we think back to that simulation, another useful way of looking at this question is rather than statistically, just looking at it geometrically or topologically and asking what the limiting shape is, right? What the attractor is. You can interpret the attractor in many ways. For instance, one way is just to think of these sets as possible attractors, right? And in some probabilistic sense. But the easiest way to think of what an attractor is just limit set of orbits against starting in some positive measure basin. And then you could do a topological version of the Palace program, and you could ask whether for a typical map and some class, the set of topological attractors is also finite. Okay. And so the answer is known in one natural class of maps, but it's a really important class of maps. Oops, sorry. So these are the quadratic family. Which are, I mean, there are different ways of parameterizing this family, but I could just write FA of x is equal to 4AX 1 minus x. So these are functions from 0, 1 to itself when A is in 0, 1. This is in dynamical systems, you know, sadly, or happily, I mean, if you're a dynamicist, that means there's still plenty of money to be earned. This is the pinnacle of our achievement. Right? So it has been the object of most of the work in the field, I mean, without exaggeration, since at least the 1970s. And in fact, in both the probabilistic and the topological sense, Palace program works extremely well for this family. And this is, I mean, that's combined work of many people, but the final theorems are due to Lubitsch. And let me maybe start with the statistical version. The statistical version is that for almost every A in 0, 1, there exists a unique physical measure such that the basin of this measure is the whole interval. Okay. And there's a topological version of this that, in fact, this is not for almost all, this is for all A in 0, 1. There exists. I should say it like this. How should I say? There exists a set. Oh, A is taken. A would be great for an attractor. B in 0, 1, such that for a typical X in 0, 1. Okay, and the typical here could be interpreted essentially in any way you like. So you could do full measure, and this is true, or you could do, second Baire category, and this is true. So pretty much however you pick a point, it is true that the limit set of the orbit of X is B sub A. And B sub A is in fact quite simple. There are only 3 possibilities. So B sub A could be is a periodic orbit or a periodic orbit of intervals. So sort of like this. Or a Cantor set, which is the intersection of periodic orbits of intervals. All right, so you have subintervals here, which are interchanged, and then subintervals of those, and so on, and the intersection is your attractor. These are the only 3 possibilities that can happen. It's really a very simple system to analyze. Okay. All right. Very good. How much time do I have, by the way? Oh, whew. I for some reason thought it's 12:40. Oh, I have plenty of time. Okay. Good. All right, so that's from the dynamical side of things, right? So what about the computational side of things? I mean, I told you that there is some difficulty potentially in computing things, but you could see that at least from the point of view of the dynamics itself, there is no difficulty. There is a nicely behaved limit and statistical distribution. In fact, there's only one physical measure, so it doesn't. You don't even have to do a Monte Carlo by sampling different points. You could just pick a point at random, and for sure it will work, right? And also in topological sense, again, you could pick any point at random, and for sure it will work, and you will get a limit set. Okay. What about computing these things? Now it's so great to be talking to computer scientists as opposed to dynamicists, so I don't have to give my embarrassing explanation of what a Turing machine is. Right? But for the few dynamicists in the back, let me say that we don't care what a Turing machine is. Its computational power is the same as that of a program, say, in Python. So think a program in Python or an algorithm, doesn't really matter. Right. So need to erase something. Suppose I can erase this. Right, but as most of you probably know, Turing in 1936 didn't introduce a Turing machine just for the fun of it. He did it to introduce what became a notion of constructive or computable analysis, which is a computable real number, right? So Turing's definition is that X R is computable if there exists an algorithm. I'm tempted to use letter A again, but it got overused. So M for machine, which takes as an input a natural number and outputs a rational. So I don't know, En and Q, such that could be dyadic rational, just a finite string of bits, such that the distance between X and Dn is bounded from above by some specific constructive bound, let's say 2 to the minus n, right? So you could compute this with an arbitrary finite precision, say in binary. And then Turing showed that by encoding an unsolvable, algorithmical unsolvable problem, specifically the Halton problem, in the bits of a real, you can produce non-computable reals, right? And that's what the name of the paper was actually about. Right, so based on this definition, it's not terribly difficult to say what a computable set is, or at least what it should be, and what a computable measure should be. So we could so for instance, a set S in a RAM is computable if there exists M such that it takes an input N and it outputs a set called Dn in a RAM. So this is an output of an algorithm. So you could think of this as a finite collection of rational points such that in a suitable metric, the distance between S and Dn is less than 2 to the minus n, right? So and the suitable metric here is the Hausdorff distance. Could I see a show of hands, those who don't know what the Hausdorff distance is? Everybody does? Ah, somebody doesn't, okay. So, right, so Hausdorff distance of two sets is the infimum of epsilons such that A is contained in the epsilon neighborhood of B and B is contained in the epsilon neighborhood of A at the same time. So this is the sense in which two pictures are similar when we say the two pictures are similar, right? So if this is a picture of a circle drawn within the limits of my artistic ability, and this is what I would do after and night out, then the Hausdorff distance is pretty small, right? You only need to blow up one of these pictures a little bit to cover the other. But if we add some features to the circle, then the Hausdorff distance will become large. Because now you blow up the pink only a little bit to cover the blue, but vice versa doesn't work anymore. Right? So, okay, so that's a definition of a computable set. You could do the exact same thing with measures using, for instance, instead of rational points, you could use finite convex combinations of delta masses at rational points. But you could also do what we usually do with measures and talk and give a dual definition, right? So you could say that the measure mu is computable. Mu is computable if there exists, well, if integrals of test functions can be computed with any finite precision. Right, so in other words, there's a machine here, it takes n and k, and it outputs I and k, which is like the integral of the kth test function. So you have some sequence of test functions. I don't know, like some higher functions that you like, and this is going to be the integral of the kth function computed with precision 2 to the minus n, right? Minus the integral of g k d mu is less than 2 to the minus. Definition of computational complexity is a little subtle because, well, because it will depend in a way of what you think of the size of your information input so it will depend a little bit on how you frame these definitions. But this is irrelevant because I'm going to only state bad results, so it's going to be irrelevant. Okay, all right, so we're ready for bad news, right? So good. No, sorry, I forget. When I talk to dynamicists, this is bad news. For computer scientists, this is all good news, right? So good news. So here are the good news. So let me erase the statement of policy program. And I would like to say that it is actually natural to conjecture that the program itself fails for reasons that are similar to reasons for the negative results that I'm going to formulate. But I don't want to go there, right? And anyway, we're talking about a family of one-dimensional dynamical systems where this is clearly true, right? So everything works. Okay, so these results are joined with Cristobal Rojas, who used to be our postdoc and is now a professor at the University of Santiago in Chile. And here are the results. Let's start with the statistical case, right? So with the statistical case, here's the theorem. So there exists, and I'll comment on this quantifier in a minute. There exist parameters A such that first there exists a unique physical measure mu sub A, right? So in that sense, life is good. And secondly, mu sub A is not computable. Okay, now the existence part. It's fair to ask whether this set is large in some sense, we don't know. Okay, so we don't know. That's an open question. I kind of doubt it for this family. It's a little too simple. I mean, it's uncountable, but it probably has measure 0 in this family. Okay, but I can't really say for sure. But it certainly contains computable values. So there is an algorithm to produce such values. Okay. So, and then also with Christabel, so there's another theorem which answers the topological side of this. And on the topological side, we can say the following. So the attractor B sub A is always computable. But it can have arbitrarily high complexity. Okay. And again, I mean, if you give me a lower bound, then I can beat it by some specific algorithm. So these could be constructed. It is an open question and an interesting one, whether polynomial time computability has full measure in this family. I wouldn't bet on it, right? So even though in practice, in theory, you can always do this. I mean, you know. Okay, so this is kind of fun. What does it actually mean in practice? Well, it means that weather prediction may not only be hard, it could be hopeless. Right? I mean, in the situation when the physical measure is not computable, it doesn't even matter what technique you will be using to try to get that 40%. Right? You will probably fail. So it's very reasonable to ask what happens in higher dimensional families, and there's every reason for pessimism for higher dimensional families. I mean, we don't know at this point. The math is hard, so but I would not be too optimistic. I would not be too optimistic about Palace program in the way I stated it, but you see, in a sense, these are somewhat unrelated issues. Because even if there are infinitely many attractors, it could still be perfectly plausible that something like a Monte Carlo simulation gives you a well-defined average, weighted average of those attractant basins, right? And that this average would be computable, and this would be a meaningful thing. I mean, maybe there are not finitely many worlds that we live in, you know, in this world, it rains today, in this world it doesn't, right? And the one in which it doesn't is only slightly bigger than this one, right? 1.5 times bigger. Maybe there are infinitely many such worlds, but we shouldn't be interested in the ones that are too small, right? We're very unlikely to find ourselves there. So it could still work. Right, but non-computability could happen even if there is only one world, and that world is nice. Okay, so I have a few minutes. I don't know if you want to see the proof. It's kind of funny, but the phenomenon is so robust that I can actually, in like 2 minutes, let me do it. It is instructive not because of the math itself, but just so you could see how robust the phenomenon is, how likely it is actually to be replicated in much less benign scenarios. So here's how you hide the Halton problem in mu. Okay, so you start by looking at a specific map. So that specific map of 0, 1. So here is 0. Here somewhere far is 1. I will also need the diagonal x is equal to y. You're looking at the map for a map which for which the critical point, which is the tip of the parabola, which is at 1/2, is pre-periodic for the third iterate. Let me explain. This sounds too complicated. Okay, so there is some point beta prime here. There's some point beta. Okay, and if I draw the graph of the third iterate of this function, restricted to the interval beta prime beta, it will also look like a parabola like this. So if you take the tip of the parabola, okay, you could see that it first goes to beta prime, then goes to beta, and then gets stuck there. Beta is a fixed point for the third iterate, right? So this is F3, F iterated 3 times. It will also help us to know that to the right of this, there's a little interval on which the second iterate happens to be a diffeomorphism whose image is the whole interval beta prime beta. Okay? All right, this is the second. Okay, nothing interesting happens for this map. This map is completely harmless. But now I would like to play the full-on game. I would like to miss beta prime a little bit by pushing the tip of this parabola down. Okay, so I'd like to take something like this. This happens if you take a slightly larger array. What will happen? Well, okay, you will miss here. It's my phone. Oh, great. So you'll miss here, and you'll land a little bit to the right of beta. Okay? After you apply the third iterate 3 times. Now here's the thing. Beta map is very expanded near beta. Look at this. The derivative here is way bigger than 1. Okay, so it's really expanded. So in particular, if I start with any point here, it will very rapidly converge into the blue and hit this blue interval. I can draw it the other way. If I draw the pre-images of the blue, they're very small and end up in a small neighborhood of beta. Okay, so here is now what's going to happen. Yellow is going to miss. It is going to hit in one of the blue. It will get into this blue, and then it gets anywhere. It's in my power to put it anywhere else in this interval. In particular, I could put it back into the same place, well, almost the same place. I could still miss beta prime, but just by a tiny bit less. Okay, then it repeats. Then it goes to beta, spends a lot more time here, eventually climbs out, hits this, goes back. I can keep repeating this, and I can, for instance, put all of the visible statistical behavior on beta. So my orbit of this point will spend so much time at beta that for this particular point, this will be the only statistics you see. And then here comes a magical fact of one-dimensional dynamics. If I then close the loop and send this point back to 0, then the statistics of this point becomes the statistics of every point. So this is now true for every point, okay? So I just made this repellent fixed point beta the limit in statistics. Monte Carlo will tell you this. It will tell you that you spend all the time here, and this will be true, okay? All right, but you see, I don't have to put it back here. There's in fact a whole invariant Cantor set here for these 2 branches of the map, and I could really charge anything on this Cantor set with whatever charges I like. So in particular, I could hide the Halton problem if I like in the way I charge the intervals in this Cantor set using the same exact scheme in many different ways, right? And in fact, any expanded invariant Cantor set for such a map would work. It doesn't have to be something that's produced by this dynamics. And that's it. So if you do that, that's going to be your limit and measure, and it will not be computable because you hit too much in it. Okay, so it's a very simple, very robust phenomenon. I went 1 minute over, I'm sorry. Okay, I'll end, thank you.